Origins and Edges of the Universe. Imagine holding the universe's first school photo in your hands. It looks strangely calm, a hazy, stippled glow that cosmologists call the cosmic microwave background, the chilled afterlight of creation spread across the sky like frost. At first glance, it is eerily uniform, as if an invisible hand smoothed the paint before it dried. That smoothness is our first riddle. To make a sky so even, the newborn cosmos must have expanded with reckless speed in a flash called inflation, space ballooning faster than light, ironing wrinkles into near perfection. The math behaves. The mechanism does not confess. What field ignited inflation? What switch flipped it off so precisely? And why did any of it happen at all? Our theories can sketch the canvas and frame. They struggle to name the painter or explain the primer. Walk one step deeper into that beginning and language starts to slip. If time itself began with the Big Bang, does it even make sense to ask what came before? Before presumes a clock already ticking. Yet the human mind keeps tugging on the curtain. It imagines cycles, universes that inflate, cool, collapse, and bounce. It imagines a foaming multiverse, a lattice of bubble universes beyond our horizon, each with its own settings for nature's constants. Maybe our cosmos is one lonely bubble in an otherwise empty sea. Maybe it is one of countless siblings, and we woke up in a hospitable neighborhood because only hospitable neighborhoods allow questions. Observation cannot yet choose a side, so the question hangs, a signpost at the edge of the map where the road dissolves into fog. A more earthly puzzle arrives early. Matter's unfair win over antimatter. The equations say the Big Bang should have forged equal twins. Equal twins annihilate into light. And yet matter eked out a tiny surplus, one extra part in billions, and the entire visible universe is built from that narrow victory. We can point to subtle asymmetries in particle decays that hint at how the scale might have tipped, but no experiment has unraveled the whole knot. Somewhere between the first fractions of a second and the birth of the first stars, the game was rigged for matter. The rulebook is missing a page. Beyond that, two invisible pillars hold everything up, and both are mysteries. The first is dark matter. We never see it directly, we see its tug. Galaxies spin too fast for their visible mass to keep them bound. Clusters bend light more than ordinary matter allows, and the large-scale web of structure grows along filaments pulled tight by invisible hands. Dark matter explains the choreography with one stroke. Add mass we cannot see. But what dark matter is remains stubbornly blank. For decades, detectors buried under mountains and embedded in polar ice have waited for a dark particle to tap on the glass. So far, silence. If that silence persists, we may be forced to ask an impolite question. Whether gravity itself needs a quiet amendment on the gentlest scales, a tweak to the grammar rather than a new noun in the sentence. The second pillar is dark energy, a label that is more confession than explanation. In the late 1990s, careful observations revealed an accelerating expansion. Space is not only growing, it is picking up speed. The simplest explanation is a cosmological constant, an energy of empty space itself. But the numbers chafe. Quantum theory's naive estimate for vacuum energy overshoots reality by an absurd factor. Dynamical fields have their own headaches. Either way, dark energy dominates the cosmic budget, a slow pressure that pushes the universe apart while refusing to say what it is made of. We put a name on the door because we don't yet have a key. Even the universe's baby photo has quirks that refuse to sit quietly in the album. The afterglow's freckles are not perfectly random. There is an oversized cold spot here, an eerie alignment of low-order multipoles there, oddities that dance on the border of statistical significance. Perhaps they are nothing but the dice rolls of cosmic variance. Perhaps they are footprints from pre-inflation physics, ripples frozen into glass before the furnace cooled. With instruments this precise, we no longer argue about whether the picture is noisy, we argue about whether the noise carries a message. Zoom out to a census and you find bookkeeping problems of a more ordinary sort. For years, a chunk of baryonic matter, the protons and neutrons that make up stars and people, went missing. The best guess, supported by careful observations, is that much of it hides as whisper-thin gas in the warm, hot intergalactic medium, threading the space between galaxies like vapor. Even there, the ledger balances only grudgingly. The everyday stuff is supposed to be easy. The universe likes to remind us that easy is a word for textbooks, not telescopes. Then there is geometry. What is the shape and topology of everything? Observations say space is nearly flat on large scales, but nearly flat leaves room for a gentle curve. Is the cosmos infinite or finite and wrap around like a high dimensional torus, where a traveler headed straight could return from behind? If the universe is finite, does it tile itself with repeating patterns we have not yet recognized? We look for matched circles in the microwave background, for echoes that will betray a hall of mirrors. So far, nothing definitive. The hallway keeps going, lights dim but inviting. Our rulers disagree as well. Two independent methods, one anchored in the early universe, one built from nearby galaxies, measure the current expansion rate and refuse to shake hands. This Hubble tension exceeds the quoted uncertainties on both sides. Perhaps there are systematics we have not fully tamed, dust we misestimated, calibrations that drift, environments that skew. Or perhaps the tension is the drumbeat of new physics, a quiet message that the standard model of cosmology needs a subtle patch in its opening paragraphs. Move forward a few 100 million years after the Big Bang, and the universe gets ambitious. Telescopes now see massive, mature looking galaxies when the cosmos was barely out of childhood. In the time budget we thought was available, how did they assemble so quickly? Where did they find the cool gas to paint billions of stars across their disks? Feedback from early supernovae and black holes should have choked star formation. Instead, some early galaxies look like overachievers sprinting before the starting pistol. Either our simulations underestimate the efficiency of star formation, or our narrative of early heating and cooling needs revision, or both. At the hearts of these young cities sit supermassive black holes, billion solar mass monsters that somehow bulked up before the buffet opened. Growing a black hole that big from the corpse of a massive star requires either incredible luck, endless meals without choking on radiation pressure, or heavier seeds. Direct collapse black holes born when pristine gas clouds fell straight into gravity's well without fragmenting into stars. There is also the possibility of super Eddington accretion, a fancy way of saying nature found loopholes that let black holes gorge faster than our simple limits predict. We have sketches of each path. The universe likely used more than one pencil. Peer inside a black hole, if inside is even a meaningful word, and general relativity draws an infinity, a singularity where density and curvature blow past anything sensible. Infinities are often signposts that say, theory out of jurisdiction. Many physicists expect quantum gravity, a marriage of the very large and the very small, to replace the singularity with something physical. Alongside that is the information paradox. If nothing escapes a black hole, what happens to the information about the things that fell in? Does it leak out encoded in a black hole's slow hawking radiation? Is it preserved on the horizon in a holographic sense? Are there firewalls where smooth spacetime should be? The debate is less about drama than about consistency. Our two best theories disagree about what is allowed, and the black hole sits between them like a referee with both hands raised. The equations that allow black holes also admit time reversed cousins, white holes, objects that spit matter but never swallow it. We have never seen one. That absence may be unavoidable. Even if white holes could exist mathematically, the universe may have no path to make them. Or perhaps they are too brief, too faint, or too rare for our instruments. The possibility is a reminder that mathematics is a dictionary. Reality uses it with an accent. Even when nothing escapes a black hole, something astonishing appears to. Relativistic jets, pencil thin beams that lance across thousands of light years. They originate not from within the event horizon, but from the extreme physics at its edge, where magnetic fields, spinning disks, and spacetime's drag twist in falling matter into coherent streams. The brightest lighthouses in the cosmos, quasars, are powered by those central engines. We know the actors: black hole, disk, field, gas. The stagecraft is still in rehearsal. How the fields thread the hole, how the disk regulates its heat and thickness, how winds, jets, and radiation divide the labor, how the engine turns on and off over cosmic time. Pull the lens back to galaxies as a whole, and the arithmetic grows argumentative. Rotation curves in many systems call out for dark matter. A handful of galaxies now appear oddly understocked or overstocked, challenging one-size-fits-all expectations. We find ultra-diffuse galaxies the size of the Milky Way, but as faint as wisps, and others that seem to lack dark matter almost entirely, claims that ignite and cool as data sharpen. Are these quirks of environment and tides, or warnings that our dark matter story has chapters we have not read? The universe writes exceptions in tidy script. Beyond any single galaxy lies a subtler drift. Our local group flows toward a murky region partly hidden by the glare and dust of the Milky Way, a gravitational sink nicknamed the Great Attractor, nested within a broader basin called Laniakea. Mapping what tugs on us is like reading an eye chart through fog. Every improvement in our catalog of galaxies peels back a little more of the zone of avoidance, but the picture remains a mosaic with missing tiles. Gravity is patient, cartography less so. There is also the question of how galaxies quench, how some switch off star formation while others blaze on. Candidates for the switch include central bars that rearrange gas, black hole feedback that heats or ejects fuel, halos that keep infall hot, that starves a galaxy by cutting off its supply, and the cosmic web itself, which can shock or shear gas as galaxies fall into clusters. The answer is unlikely to be singular. It will be a choir, with different voices dominating in different environments and epochs. Threaded through all of this are cosmic voids, enormous underdense regions spanning hundreds of millions of light years. Simulations produce them naturally, but the real voids carry subtleties. Their sizes, shapes, and the way they lens background galaxies and imprint themselves on faint temperature maps of the micro background. Voids are not empty. They are repositories of delicate information about how structure grows and how gravity and dark energy share the work. So the first act ends where it began, with a map that holds magnificently in broad strokes and puckers at the seams. The LCDM framework, dark energy, cold dark matter, CDM, general relativity, paints a convincing mural of cosmic history. But at every joint, the cosmos leaves a question mark instead of a rivet. That is not discouraging. It is a feature. A good map shows you where you are and, more importantly, the blank spaces that invite expeditions. In the next part, we leave the scaffolding of spacetime and walk into the furnaces and ruins, stars that live by fusion and die by spectacle, collisions that ring spacetime like a bell, and a menagerie of worlds that break the rules with a smile.